So here we are, lesson 69. We're going to do a number of applications working with exponential functions and derivatives and build off of what we looked at yesterday. Okay, it's kind of small there, but here we have the function f of x equals x times e to the x. Don't forget, how are we going to take a derivative of this? Product rule. Okay. How do I know I'm going to take a derivative of this? Yeah, anytime I see this idea, relative extrema or relative max or min, I need to think derivative. Okay, so f prime of x, using our product rule, we have the derivative of x is 1 times e to the x plus x times the derivative of e to the x is e to the x. Okay? So, f prime of x equals e to the x times 1 plus x. And that's important because we're trying to find relative extremis, so we take the derivative and do what with it? Set it equal to 0. We solve it for where it equals 0. Now guys, here's where knowing your domain and range of the parent function is important. Because when will e to the x equal 0? Never. Remember, the range of e to the x was everything greater than 0. Okay? So this, we're not going to get any critical value from. We're only going to get one critical value, and that is when x equals a negative 1. Okay? So that is our x coordinate. So I know there is something there. Let's see if that is a max or a min. We have, if I plug in, say, a 0, I have e to the 0, which is 1, and I have 1 plus 0, which is 1, so that's positive. So it looks like this is going to be a min. Let's check and make sure it's not a plateau point. If I plug in a negative 2, e to the negative 2e is always positive. Okay, 1 minus 2, though, is negative 1, so I know that that is negative, so my function is decreasing. Okay, so that means that we have a relative min at negative 1, and then we just got to get the answer to what that is. Negative 1 times e to the negative 1 is just a negative 1 over e. Okay? So there's our point. Again, be careful. Saw this on our FRQ. We saw this on the last quiz in the multiple choice. Be careful that you give what it actually is, okay? If it's asking for an extrema, go ahead and give the whole point, okay? If it's asking for the min value of the function, they're looking for the y coordinate, okay? Not the independent variable, not just the x or the t or whatever. They're looking for the value of the function, okay? If they might, though, ask for what x coordinates or for what values of t do we have a min. There, don't bother doing work you don't have to. Once you get it, just say your answer. Okay? All right, now.
Why is it negative 1 over e? Because when you do 1 minus 1 is 0 and you're multiplying it.
Well, hang on. Yeah, we're looking for a point on the graph, so we're not plugging it into the derivative.
Oh, the record.
We're plugging it into the original. Okay? It should equal 0 if we plug it in the derivative, because that's how we got it. All right, if you look at the function here, you actually can see, okay, there's the graph, there's the relative min at negative 1, negative 1 over e. Okay, that's what that graph would look like. Yes?
So, for the horizontal asymptote, it still approach to 0?
This one does actually still approach 0 as x goes to negative infinity. Yeah. Yeah. Remember, horizontal asymptotes are different than vertical asymptotes. Here, it actually does hit the origin.
Oh,
So horizontal asymptotes you're allowed to actually hit somewhere in the middle, but horizontal asymptotes are all about the end behavior. What's happening as x goes to positive or negative infinity? Okay. All right, let's take a look at another one. This is kind of a cool one because, like, you guys have worked with bell curves before, probably like in psychology or in science or something like that. But a lot of times we've never seen where that curve actually came from. And here's actually the normal probability density function. That's what the name of the function that gives us the bell curve is. Okay, you can actually see down here the general form. Sigma is the standard deviation, okay? And actually this is even a simplified version that's centered with a mean of 0, okay? If the mean was something else, it would be negative parentheses x minus the mean squared over 2 sigma squared. Okay, so that even is a simplified version of what it's actually doing. So kind of interesting thing there, all right? But here it's, notice the image here says that we have 2 points of inflection at 1 and negative 1. Let's prove that, okay? Let's prove that. If I'm looking for points of inflection, what automatically comes to mind? Second derivative. There we go. Second derivative equal to 0. Those connections are, we got to be really good making those connections between the language and what we got to do. So, first derivative. This whole mess in the front is just a constant, so it's going to stay put. 1 over radical 2 pi. But then we have to multiply by that derivative of e to the negative x squared over 2. So, that's e to the negative x squared over 2 times
Negative x to 1. This is a negative 1/2 x squared, so you bring down the
it's negative 1/2 x squared, so what's the derivative of negative 1/2 x squared? Negative x, yeah.
Oh,
Okay.
2 minus 1.
So it'd be negative 2 times x over 2, so the 2's will cancel. Okay? Now, in order to help us out here a little bit, let's simplify. I'll put the negative over with the constant. So we'll make that a negative 1 over radical 2 pi x times e to the negative x squared over 2. And now to do the second derivative, I've got to use what? Product rule, okay? Now, I still have that constant, so I'm going to write that down and then do the product rule. Okay, I'll just put that in parentheses here. So u prime, well u is x, so I'm just going to put a 1 there, times v, e to the negative x squared over 2, plus u, which is x, times v prime. Well, we just did the derivative of e to the negative x squared over 2 on the previous step. So we don't have to think too hard. It's going to be another negative x e to the negative x squared over 2. Okay? Now I notice that I have a common factor here of e to the negative x squared over 2, so I'm going to pull that out. So now I'm going to have a negative 1 over radical 2 pi e to the negative x squared over 2 times, what's left over in the parentheses? 1 plus a negative or 1 minus x squared. Now question, when is e to a power 0? Never. Okay? E to a power is never 0, so I know I'm not going to get any critical values from that factor. But if I set this equal to 0, I will get x equal to plus or minus 1. Okay? if I do a sign diagram for this, I put -1 and 1 on here. Okay. Also, so the second derivative, if I were to plug in anything to e to a power, I know it's going to be positive, right? So I have here a negative times a positive times whatever's in the parentheses. So if I plug in, say, a -2, I'm going to have 1 minus 4, which is negative. So I have a negative times positive times negative. So that's positive, and that means I'm concave up here. If I were to plug in a 0, I'd have a 1. So negative times a positive times positive gives me a negative. So there it's concave down. So we just proved that -1 is a point of inflection. And now, if I plug in a positive 2, I'd have 1 minus 4 is negative times a positive times a negative. That's going to be positive again. So yes, both of those are points of inflection. Okay? If you happen to recognize this as an even function, we would have known as soon as we knew -1 was a point of inflection. But okay, so we just showed that since concavity changes, x equals plus or minus 1 gives points of inflection. Okay. So let's look at one more here, an example with an exponential growth function. Okay. The number of medical doctors in the United States. Okay, so Y is the number of medical doctors in thousands in the United States from 1980 through 1997. Can be modeled by Y equals 475,520 e to the 0.0271 t. Okay, got a little bit messed up here. Okay, that's 0.0271 t. All right. Okay, so at what rate was the number of MDs changing in 1992? Okay, so first of all, what exactly are we looking for? A rate of change, which is derivative. Okay, so we want the derivative when? At what value?
T equals 0.
1992, so t equals 0 is 1980, so 92 would be 12. Yeah. If they made 1 1980, then yeah, it'd be 13, but we try to avoid confusing you. Alright, so y prime of 2 is really what we're looking for. Once you guys identify that, the whole thing isn't that hard, okay? But you want to make sure that you're identifying exactly what you're looking for, okay? So let's first of all find y prime, okay? Y prime equals, okay, we have 475, 520. By the way, I know some of you read the comma as the decimal point. That's not what it is here, okay? If you grew up switching those. Alright, that's 475,520. Then e to the 0.0271 t times, good, the derivative of that is 0.0271, okay? So we need to multiply that. Okay, So we have 12,886.592. By the way, here's a good example. We're dealing with two rational numbers, and the decimal goes, I know it only goes 3, but even if it went 4 decimals or something, since it stops, doesn't keep going forever, go ahead and use the whole thing to get the most accurate answer. Don't round. Okay? So now we have that, and now to get our answer, we're going to plug in 12. Okay? So we do that times e to the 0.0271 times 12 power, and we get 17839.006 if we round. Okay?
Would you say MDs per year?
Okay, now here's where you got to be careful with your units of measure.
Thousands per year.
Thousands of MDs per year. Yeah. And this is where, go back, remember slope is rise over run. So the rise is your y coordinate. What is the unit of measure there? It's thousands of MDs. Okay? So thousands of MDs per time here is measured in years. So per year. Okay, that's the rate of change in 1992. Okay?